Here we are in the TWR software solutions. Previously, during memorandum control, I show you this plot and say to you that we want to replicate this time history acquired into the control channels during memorandum here in TWR. Anyway, this plot show also the starting step. As you can see, we have the first step here at -6 dB for 10 seconds, and then the second step at -3 dB, and then the full level. What we want to do is just to replicate the full level test. Okay, so I already cut the time history, the signals, just to have the last 40 seconds, so the full level test. Okay, and therefore we try to replicate and we try to control this time history in the control channel here in TWR. So let's start and go in channel setup. The channel setup is the same for the memorandum, so our control channel here, the measurement one here, and all the stuff is the same, so I can skip in the TWR setup. Here we have to define some acquisition parameters and define, of course, our test specifications, so our control target traces, our time histories. Okay, so let's start with activate our shakers here, put the direction, and then the limit, the voltage limit. Then we can go here on the right in the control panel and set the bandwidth 1600 is okay. The resolution 1.5 is the same for the random control test, and then set the minimum and the maximum frequency, so 9.38 and 500, the same as memorandum. Of course, the bandwidth 1600 is okay because it is more than 2 times the maximum frequency. Okay, then we can skip here to define our control target trace. We click on search data selection and into memorandum 0 dB that are the time history acquired during memorandum. Then click on OK. Then we have to set some parameter here. The fade in, fade out in second 0.1. It's okay. The fade in allow you to force a smooth transition from 0 at the beginning and to 0 at the end of the target trace. As a starting frequency 9.38. 500 as a F max. With this value we specify a bandpass filter to apply the selected target trace, and then the scale factor 1 is okay. Here on the right we can have a look about some parameters. For instance, the X direction we have a duration of 40 seconds with more or less an RMS value of 1G, of course. The same for the Y direction and the Z direction. We can skip on time just to see our target tracing time domain, of course. Okay, and then in frequency domain with the PSD we have our white noise along the Y direction, then the white pink noise for the Y direction, and the blue white noise in the Z direction, of course. Now our control target trace are green. It means that the status is okay, and therefore we can skip into the system identification section in order to identify our control system and therefore to estimate the transfer function between the inputs and the output. So here we put 10 as a number of averages, the same that we have put in memorandum, pseudo-random and random, okay. All the other settings are okay, so I click on ARM. And then start. Here you can see our drive signals from the shakers. The PSD are flat PSD, white noise, and here our responses. Okay, the PSD. Or the transfer function. Okay. Now we have estimated our transfer function and identify our system, and therefore we can skip in system verification. Here the layout is quite a bit different with respect to memorandum. Anyway, we can view our data. Here the inverse FRF, so the impedance of our control system, and as before we have at 240 our anti-resonance, okay, that probably caused some problem during the control test. Anyway, we can go on the TWR drive tuning. Here first of all we go on the setting subsection, because we have to define some of the control parameters. First we set here the maximum number of iteration, and we can put 10. Okay, it means that the control algorithm will perform 10 iterations by replicating for 10 times our reference time histories, and of course it will try iteration by iteration to reduce the error between the reference traces and the measurement one. Then here in the control channel parameters we have our control channel, and we have to set other control tune parameters. For instance, here in the first drive 50% it's okay. It means that the first iteration will start at 50% with respect to the full level reference traces. This is always for safety reason, because starting from the full level could be dangerous for our test equipment or spacemen, and therefore could be better to start with 50% and to increase the level iteration by iteration. Then here in convergence we can put 10%. Okay, it means that if the calculated error between the reference and the measured traces is below the 10% in all the control channels, the drive is considered tuned and the iteration will stop. Therefore, for instance, if we reach the convergence at iteration 6, the test will stop also before the end of the 10 iterations, because it means that we have reached our goal and we have perfectly replicated our time histories. The same here for the divergence. If the error is higher than this value, we can put 100%. So if the error is higher than the 100%, means that the control action is diverging, and therefore something is going wrong and the iteration will stop. The delta divergence instead is between two different iterations. If the error increase of this value between two iterations, two different iterations, the actual iteration will stop, always for safety reasons. Instead, here in the error correction parameters, you can set some value that influence the way by which the drive error correction will happen iteration by iteration. I mean, you can set the percentage of error that should be taken into account for calculating the drive correction. Anyway, in our case, the default value are okay. So here we have set everything, and we can come back to the acquisition subsection. Here we have different displays for different plot types. Before to run the control test, I want to explain you. Here in the first plot, you will see the sliding time history of the measured and the reference signals, so in time domain. In the second one here, the PSD, so in frequency domain. This one instead plots the measured signal along the X and the reference one along the Y in a one-to-one scales. It means that if you look a straight line along the bisector of this graph, you are reaching the convergence, and the control is good. The last plot instead is like a gauge with the end here that say to you the error percentage. The red part is for the divergence values. Instead, the green part is for the convergence. Now, if I skip to 3 channel, we have the same plots here for our 3 control channel, and if the end of the gauge is in the green space for all the channels, the test will stop because it means that we have reached our goal. Okay, now we can arm our shaker. And then click to start. Now the shaker is running. As explained before, the test started from the 50% of the full level, as you can see here in the PSD plot. The green line is our full level target. The blue one instead is the measure. Here you can see, of course, the time domain. In time domain, the time history. Now we are in the second iteration. You can see here the ongoing iteration. The PSD level is increased. Now we have more or less 25% of error in all the channel. Okay. Now we are in iteration 3. The error is slowly decreasing, and the better is the control and the more aligned this curve is. I mean, along the bisector, of course. I can also increase here just to better show you the time histories between the measured and the reference one. Now we are in iteration 4, and we have reached our convergence here in direction Z and Y, but not here in the Y direction. Probably is here at these frequencies because we have our anti-resonance. Okay. This is iteration 5. Now we have reached our convergence in all the channels, so it means that at the end of this iteration the test will be stopped. And here we are, convergence reached. Okay, so the test is a normal and control test, and then we can skip into the navigator to show the result. So here we want to compare the result obtained with MIMO-random and TWR in the measurement channel. So we can create a plot here. Okay, we take the PSD measure during MIMO-random. Okay, and then the one in TWR. So iteration 5, the last iteration, we go in the measure fold, average PSD, accelerometer 2, X, Y, and Z. As you can see, globally we have obtained the same result in the measurement accelerometer by using MIMO-random and then the TWR, and therefore we have completed this analysis with these two different vibration control techniques. So we can skip into the last one, the MIMO sweep sign. This is MIMO sweep sign testing, another available solution for vibration control testing in SimCenter Test Lab. Here we want to perform sweep sign control in 3 directions simultaneously. In particular, we want to control our triaxial accelerometer fixed on the top of the head expander, and at the end we want to check the transfer function between the control accelerometer and the measurement accelerometer in order to evaluate possible resonance on our EGR valve. So let's start with the analysis. First of all, here in channel setup, the channel setup is as always the same, the one for MIMO-random and the TWR. So I can easily skip into the MIMO sign setup section. Here we have to define the parameter for our analysis. So first of all, we activate our shakers. We put the direction and the maximum level in voltage, as always 8 volt. Then we can skip here on the right just to set some parameter. Here in the sweep panel we set the minimum and the maximum frequency, so 10 Hz to 500. The frequency resolution to Hz, it's okay. And then the sweep mode, we can choose from between linear and logarithmic. If you choose linear, all the settings are in Hz per second. With the logarithmic case, is octaves per minute. Linear, it's okay. Then the sweep direction, up or down, depending. If we choose up, it means that your sweep sign goes from low frequency to high frequency. Then the sweep rate, number of periods, fixed sweep rate, we can put here maybe 20 Hz per second. Now our single sweep time is 28 seconds. We can change here the number of sweeps, put 3, because the minimum number of sweeps correspond with the number of control channels that we have. So we have just 3 control channels, so 3 is the minimum number of sweep. Then between the individual sweep there will be a phase shift for the drives. This is necessary, to calculate the FRF. So here we can click on phase and we define the phase shift between the drive signal for the different sweep. We can try with random. So we have phase randomization between each single sweep. Okay. So I click close. Now we have 3 number of sweeps, so the total test time is 1 minute and 25 seconds. And then here in measure we can activate instructor, auto power and FRF. Okay. Then we have to define our reference profiles. So the spectrum of our control target. Let's start with the one in X direction. So here plus X. I click on edit reference profile. Here we have our table. Here in frequency I put from 10 to 500. And we can define our spectrum in terms of acceleration, velocity or displacement. We choose the acceleration and we put 0.3 G. Okay. Then we skip on the Y direction, edit reference profile, and we put the same value. So 10 to 500, 0.3 and 0.3. Okay. And then the Z direction, 10, 500, 0.3, 0.3. Okay, now we have defined the reference profile of each control channel. So the reference spectrum for the X, Y and Z. As you can see, we have defined a flat spectrum because we want the same energy level at each single frequency. So it means that our sweep sign is composed by a lot of single sign for different frequency but with the same amplitude. Okay. Now we have defined all the setting and we can skip into the system identification section. Here, as always, we have to identify our control system by exciting the structure with decorrelated white noise drives and try to estimate the relationship between the inputs, so our drive and the output, our responses. So here in the measure panel we set the number of averages, so 10, then pseudo random random, and we click on ARM. And then on start. Now our shaker is running. These are our flat PSD for the drive of our shaker, and here the transfer function between the inputs and our output. Now that we have identified our system, we can skip into system verification section. Here we have, as always, check our data. just to see if the status of the responses are all okay, and then also the drive status to check if the power required by the shaker is available by our excitation system. And therefore, because of everything is okay, we can skip into the MIMO sign acquisition section. And here we can perform our sweep sign control test. So I arm my shaker. Okay, just a second. And click on start. Now the first sweep is running. You can see here. Okay, keep in mind that this vibration control technique is not feedback controlled, so it based just in the first drive definition. Therefore, the control algorithm doesn't calculate the error. Here, the second sweep. In this case, the control algorithm have randomized the phase shift between the drive signals. And now the last sweep. Okay, now we have done with our sweep sign control test, and we skip here in the navigator to show the result. So here in our run fold we have all the data, so the three sweep 1, 2 and 3 with the randomization phase between the drive between each sweep. But what I want to show you is the transfer function between the control accelerometer and the measurement one. So I click on a bow diagram and then I put this transfer function. Okay, as you can see, if I remember well, we have this peak at 100, more or less 60 Hertz. Okay, we had the same peak also during memorandum and the TWR, and therefore this probably is a resonance of our EGR valve. You can see also the phase change here of 180 degree. So we have done also with MIMO sweep sign. We have already seen all the vibration control techniques, and therefore that's all also for this experimental activity. And thank you for the attention.